Hi, everybody. It's Professor Mitchell. We have finally reached the last section of Chapter 2, which is 2.8 on solving linear inequalities. You may notice this PowerPoint looks a little different, and that's because I think what happened was when I first started using PowerPoints in about 2015, I don't know what happened. I ran out of time or something and did not get around to creating one for this section. Ever since then, I've used this one that originally came from the publisher. I think I've made some tweaks to it. Anyway, so when we talk about linear inequalities, we're talking about an inequality, which is a statement that contains one of the symbols. There should be the word one in there. Less than, greater than, less than or equal, or greater than or equal. So here you see a couple of equations. An equation, of course, is anything that contains an equal sign. X equals 3 and 12 equals 7 minus 3y are equations. X is greater than 3 and 12 is less than or equal to 7 minus 3y are inequalities. So when we solve an inequality, there are a couple of different ways to write the solution set. One way is with a graph. So to graph solutions to linear inequalities in one variable, we use a number line. And then we use a bracket at the endpoint of an interval if we want to include that point. We use a parenthesis at the endpoint if we don't want to include that point. And you'll see lots and lots of examples of this. So for example, here is a graph of the set X such that X is less than or equal to 7. It's a little hard to see on here, so I do have some examples that I'm going to do on the tablet. You'll be able to see it better. Here's the bracket at X equals 7. And then on the left side of 7, it's colored blue. Okay. Again, you'll be able to see it better when I draw it. And this is a graph of the set of X such that X is greater than 4. Notice the parenthesis at -4, X such that X is greater than -4. I might have said 4. And it's colored to the right of -4. Another way to represent the solution set of an inequality is with what's called interval notation. So the advantage of interval notation is that it contains all the same information that you get from the graph, and it's a little easier to write. It just takes a little bit of practice, understanding how to write it and also understanding how to read it. So if you take the graph of the set of X such that X is less than 3, which looks like this, in interval notation, that would be written with a parenthesis, -infinity, comma 3, and then a parenthesis next to the 3. The parenthesis next to the 3 means that the 3 is not included. The -infinity on the other side means that the graph goes forever and ever to the left towards -infinity. -infinity or infinity, when it's part of an interval, always gets a parenthesis next to it because infinity and -infinity are not real numbers. So it wouldn't make any sense to include them. That's an example of what's called an unbounded interval. Here's an example of a bounded interval. The set of X, really, I read this as between -2 and 0. If you were looking at this for the first time, you might read it as -2 is less than X and X is less than 0. This is called a compound inequality, and we're going to talk about those more later. But it really means that X is between -2 and 0. So that graph looks like this. And the interval notation for that is just parenthesis, -2, comma 0, parenthesis. They both get parentheses, because neither one of the endpoints is included. All right, here's another bounded interval. Negative 1.5 is less than or equal to x is less than 3. So that means x is between negative 1.5 and 3. Negative 1.5 is included, but 3 is not included. So here's what the interval notation for that set looks like. Notice the bracket next to the negative 1.5 and the parenthesis next to the 3. All right. So first example of a graph, x is greater than or equal to negative 1. Because or equal is included, we put a bracket at negative 1. And then the numbers that are greater than negative 1 are to the right of negative 1, so they are colored in blue. All right, now to solving inequalities is similar to solving equations. There's one big difference, which we will get to on the next slide. This part works exactly the same. This is called the addition property of inequality. And it says that if A, B, and C are real numbers, then A is less than B, and A plus C is less than B plus C are equivalent inequalities. In other words, they have the same solution set. So just like with equations, you can add or subtract any real number on both sides of an inequality without changing the solution set. Now, when it comes to multiplication, that's a little more complicated. If A, B, and C are real numbers and C is positive, then A is less than B and A times C is less than B times C are equivalent inequalities. So when we use the multiplication property of equality for equations, we did not have this requirement that the number we were multiplying on both sides had to be positive. Okay, so if that number is positive, then it works basically just like with equations. However, very, very important, if that number C is negative, then let me turn on my pen here. A is less than B and A times C is greater than B times C are equivalent inequalities. Moral of the story is that when you multiply or divide both sides of an inequality by a negative number, you have to reverse the inequality symbol. Okay, and you will see me do that in at least one example, maybe more, probably more. All right. So the steps for solving linear inequalities are just like the steps for solving equations. Step one, if you have fractions, it's a good idea to clear the fractions by multiplying both sides of the inequality by the LCD. Step two is to remove grouping symbols, such as parentheses, by using the distributive property. Step three, combine like terms on the left side, combine like terms on the right side. So far, exactly the same steps that we talked about for equations back in section 2.3. All right, in step four, you're going to write the inequality with the variable terms on one side and the numbers on the other side by using the addition property of inequality. And finally, get the variable alone by using the multiplication property of inequality. All right, so our first example, first real example is to solve the inequality 3x plus 8 is greater than or equal to 5, and we are going to graph the solution set. So let me go over to the tablet. All right, so quickly going through the steps, we don't have any fractions, we don't have any grouping symbols, we don't have any like terms on the left side or on the right side. So steps 1, 2, and 3, nothing to do there. In step 4, we get numbers on one side, variables on the other side. So the only thing to do there is to subtract 8 on both sides. This is using the addition property of inequality, which is going to leave us with 3x is greater than or equal to -3. And now we're going to get the variable by itself by dividing both sides by 3. And that is going to leave us with x is greater than or equal to -1. In this problem, they just wanted a graph. Okay, so let's go -2, -1, 0, 1. I don't really care how many numbers you label there. And actually, I think we looked at this graph once already, this exact same graph. Greater than -1 is on this side. And because we're also including -1, we put a bracket there. Okay. So that's all they want in this problem. In some other problems, they're also going to want interval notation. All right, so let's go back to the presentation. Okay, let's see. Okay, so the next example is to solve the inequality 3x plus 9 is greater than or equal to 5 times x minus 1. Okay, so first I'm going to do this on the tablet. It was kind of funny when I was getting ready to do this presentation. I noticed that I had the written out solutions in some of these problems, and in others I didn't. Okay, and so it turned out for this problem, I had left the written solution in there, and then I didn't realize that, and I wrote it on the tablet. But anyway, I was happy I did that because I want to show you 2 different ways you could do this problem. Okay, the way I would do it, first of all, again, no fractions in step 1. However, we do have one set of grouping symbols, so we will get rid of those in step 2. That'll give us 3x plus 9 is greater than or equal to 5x minus 5. There are no like terms on the left side, no like terms on the right side, so nothing to do in step 3. However, in step 4, that's where we have to get the variables on one side and the numbers on the other side. I have a suggestion when it comes to inequalities. My suggestion with inequalities is to put the variables on the left side. And I'm going to tell you why. This comes from experience and watching students do it both ways. I'm going to show you the other way to do it after this. Okay, so if I specifically go to put the x's on the left side, I end up with -2x plus 9 is greater than or equal to -5. So now I'll add 9, or I'm sorry, subtract 9 from both sides. And that'll give me -2x is greater than or equal to -14. Now, to get x by itself, I need to divide both sides by -2. So what's the super important thing I have to remember? Because I'm dividing both sides by a negative number, I have to reverse the inequality sign, and then 14 or -14 divided by -2 is +7. I think they said they just wanted us to graph this one, right? Well, we'll see when we go back to the presentation. So if we go like 5, 6, 7, 8. Okay, x less than 7 is to the left side of 7. And once again, I'm going to put a bracket at the 7 because the 7 is included. Okay. All right, I think that most of you will have an easier time doing it that way, specifically putting the x on the left side. I want to show you the other way you can do it, and that's already written out in the presentation. Let's see. Okay, so it starts out the same way. And now they're putting the X's on the right side. So this is another way to do it. That would give you 9 is greater than or equal to 2x minus 5. Then we would have to add 5 to both sides, which would give us 14 is greater than or equal to 2x. Now, the advantage of doing it this way is that in the next step, you're going to divide both sides by 2. And since 2 is a positive number, you don't have to remember that weird rule about switching the inequality sign. However, what you do have to realize is that 7 is greater than or equal to x means the same thing as x is less than or equal to 7. And I will tell you from experience that students tend to mess up this transition here more than they mess up switch the inequality sign when you divide by a negative. So I'm just telling you, that's what I've found. All right. But it's up to you. You know, just figure out which way works for you and then go with that. Okay. And yes, I see now that the directions were just the graph. They don't want the interval notation yet. Okay, the next example is 7 times x minus 2 plus x is greater than negative 4 times 5 minus x subtract 12. This might be a good one for you to pause the video, try it, and then come back and compare notes. I will go ahead and share my tablet. Okay, so I'm counting on you to have tried this problem already, which means maybe I'll do this one a little faster. Good thing about watching this on a video is you can pause it anytime you need to think about something. All right, distributing the 7, we get 7x minus 14 plus x is still here. Distributing negative 4, we get negative 20 plus 4x, right? Minus 12. And now there are some like terms on the left side, and there are some like terms on the right side. So that gives us 8x minus 14 is greater than 4x minus 32. It doesn't matter if you write 4x minus 32 or negative 32 plus 4x, they mean the same thing. Now I'm going to subtract 4x on both sides, which gives me 4x minus 14 is greater than negative 32. And now I'm going to add 14 to both sides, which is going to give me 4x is greater than negative 18. And then I will divide both sides by 4, which gives me x is greater than negative 18/4. So you would just need to simplify that fraction. It simplifies to negative 9 halves. And I think they wanted a graph in this one also. Okay, so just notice that negative 9 halves is the same thing as saying negative 4.5. So if I go say negative 6, negative 5, negative 4, negative 3, negative 9 halves would be right in the middle of negative 5 and negative 4. Oh, squeeze that in there. And then, oh goodness, I messed up. Shoot. Okay. I almost didn't notice it says greater than. That means it does not get a bracket, it gets a parenthesis. Because the -9/2 is not included. But all the x's that are greater than -9/2, they are to the right. So those are the ones that get colored in. All right. Back to the presentation. Okay. Okay, yes, it said graph. All right, so now we'll look at some compound inequalities. A compound inequality contains two inequality symbols, such as this one here. And technically what this means is that 0 is less than or equal to 4 times 5 minus x, and 4 times 5 minus x is less than 8. It means that both of those things are true at the same time. By the way, we will be talking some more about compound inequalities when we get to chapter 9. Okay, but the easiest way to solve a compound inequality is to perform the operations simultaneously to all three parts of the inequality, the left, the middle, and the right. Okay, so for example, this one is already solved. There is nothing more to do here. X is between -2 and 5. The -2 is not included, but the 5 is. So the graph of that set would look like this. You would have a parenthesis at -2 and a bracket at 5. And I can barely even see that. It's colored in between. Okay, so the next three examples are all on the tablet. Let me just make sure that they all have the same, they do. They all have the same direction. So I'm just going to switch over to the tablet and stay there for the next three examples. These ones all say graph the solution set and write it in interval notation. This one's very easy. The only thing that's keeping z plus 5 from being z is the plus 5. So we're going to do -5 on all three parts of the inequality, which gives us 4 is less than z is less than 8. Again, remember that means z is between 4 and 8. 4, 5, 6, 7, 8. Okay, so parenthesis at 4, parenthesis at 8, color everything in between. And then I always recommend drawing a graph before you write the interval notation, because it's very easy to get the interval notation from the graph. Just remember, the first number is where it starts, the second number is where it stops, and then put either a parenthesis or a bracket next to each number to indicate whether it's included or not. Neither one of these is included. So there's your graph and there's your interval notation. Next example. -7 is less than 2p minus 3 is less than or equal to 5. I'm going to add 3 to all three parts, which gives me -4 is less than 2p is less than or equal to 8. And then I'm going to divide all three parts by 2, which is going to give me -2 is less than p is less than or equal to 4. So the graph of that would look like this: -2, -1, 0, 1, 2, 3, 4. Parenthesis at -2, bracket at 4, color everything in between. And then you see how the interval notation is going to look like for that, right? It would be -2, 4 with a parenthesis here and a bracket there. All right, last example in this batch. 0 is less than or equal to 20 minus 4x is less than 8. I will start by subtracting 20 from all three parts. Which gives me negative 20 is less than or equal to negative 4x is less than negative 12. Then I have to divide all three parts by negative 4. All right, danger, danger. What do I have to remember to do? Because I'm dividing by a negative, that's going to reverse all of the inequality symbols. All right, now, I don't know how often that's going to happen, but typically when you write this compound inequality notation, you write the numbers from smallest to largest. And you always do that when you write interval notation. So I would strongly recommend, actually, I'm going to go a step further than that. You really have to rewrite this as 3 is less than x is less than or equal to 5. I mean, just think about the number line. If the numbers were in reverse order, that would look kind of weird. So let's go 2, 3, 4, 5. Okay, parenthesis at 3, bracket at 5, color what's in between. Okay. Interval notation is not correct unless the smaller number is written first. Okay. Do not write bracket 5, comma 3 parenthesis. That is bad notation. Your online homework will definitely mark that wrong. All right, I think we are pretty close to being done with this section. Yes, okay, so now we just get into a couple of little application problems, starting with what I affectionately call a who cares problem. 6 times a number decreased by 2 is at least 10, and we want to find the number. First step is to understand the problem. If we let x be the unknown number, 6 times a number translates to 6x. Decreased by 2 means subtract 2. Okay, this takes a little bit of explanation. Is at least 10 translates to greater than or equal to 10. A lot of people don't believe me when I first tell them that. They hear the word least and they think less than. But my favorite analogy for that is you have to be at least 21 to drink, which means your age has to be greater than or equal to 21, right? At least means greater than or equal to. Similarly, at most means less than or equal to. All right, so the inequality for this problem is 6x minus 2 is greater than or equal to 10. So we will solve that inequality by adding 2 to both sides and then dividing both sides by 6. And that gives us x is greater than or equal to 2. Interpreting the solution. As a check, they recommend replacing number in the original statement of the problem with a number that is 2 or greater. And they used 2. 6 times 2 decreased by 2 is 12 minus 2, which is 10. That is a true statement. 10 is greater than or equal to 10. It might be a good idea to also plug in a number that's bigger than 2, just to make sure the inequality is going the right way. But that is the correct solution. All right, last example. You are having a catered event. You can spend at most $1,200. The setup fee is $250. And then they're going to charge $15 per person. That's pretty cheap, actually, for a catered event. Find the greatest number of people that can be invited and still stay within the budget. Okay, so if X represents the number of people, we do the setup fee, which is $250, even if nobody shows up, and then add the cost per person times the number of people. And that has to add up to be less than or equal to 1,200. Remember, at most means less than or equal. So that turns into 250 plus 15x is less than or equal to 1,200. Subtracting 250 on both sides gives you 15x is less than or equal to 950. Dividing both sides by 15 gives you x is less than or equal to 63.3. Now, how would you interpret that answer? How many people can you invite to this event? Well, you can invite 63.3 people, right? So that means the most number of people you can have is 63, and you'll have a little bit of money left over. But if you invite 64 people, you're going to go over budget. So 63 people or fewer. And that does it for section 2.8, and that does it for chapter 2. So we'll see you next time to start chapter 3.